Hello and welcome to the Sleepy Astronomer. Tonight, we're exploring the James Webb Space Telescope through 127 carefully chosen boring facts. The James Webb Space Telescope is humanity's most ambitious eye on the cosmos, a golden mirror that peers deeper into space and time than we've ever managed before. This remarkable machine sits in the cosmic dark, collecting ancient light from the very edges of the observable universe. If you're settling in for the first time, welcome aboard our journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Wherever you are tonight, settling in for rest or simply curious about our greatest space telescope, I'm so glad you're here. Where might you be listening from as we begin tonight's journey? If this journey through the facts of deep space observation helps you unwind or fills you with quiet wonder, feel free to like the video and subscribe for more gentle explorations of cosmic discovery, distant galaxies, and sleep. It means the universe to me, and it helps build this wonderful community of curious minds and starlight admirers. So, find your most comfortable position, and let's begin our gentle journey through 127 boring facts that paint the portrait of humanity's window into the ancient universe. Fact 1. JWST is the largest space telescope ever launched. When we speak of the largest space telescope ever launched, we're not just talking about impressive engineering. We're talking about humanity's boldest attempt to see further into the cosmos than ever before. This golden giant represents the culmination of decades of dreaming, planning, and building, a testament to our species' irrepressible curiosity about what lies beyond our small blue world. Every component was designed to push the boundaries of what's possible when we point our most sophisticated instruments toward the stars. Fact 2. Its mirror is 6.5 meters across. Picture a mirror nearly 22 feet in diameter, larger than most living rooms, yet engineered to unfold with precision in the vacuum of space. This isn't the kind of mirror you hang on a wall. It's a technological marvel composed of hexagonal segments that work together as one perfect surface. When fully deployed, this golden expanse becomes humanity's most sensitive eye, capable of gathering ancient photons that have travelled billions of years to reach us. Fact 3. JWST's mirror is about 3 times bigger than Hubble's mirror. The comparison to Hubble helps us grasp the magnitude of this achievement. Where Hubble's mirror measures 2.4 meters across, JWST's massive collecting area allows it to gather roughly 7 times more light. It's the difference between looking through a telescope and looking through a giant's eye. Suddenly, the faint and distant becomes visible, the impossible becomes routine, and the edge of the observable universe draws tantalizingly closer. Fact 4. JWST mainly observes in infrared light. While our eyes see visible light, JWST sees the universe in infrared, the warm glow of heat that reveals secrets invisible to human perception. This infrared vision allows the telescope to peer through cosmic dust clouds that would otherwise hide star formation, and to see light from the most distant galaxies that has been stretched red by the expansion of the universe. It's like having thermal vision for the cosmos, revealing the hidden warmth of creation itself. Fact 5. JWST was launched on December 25th, 2021. Christmas Day 2021 became humanity's greatest gift to itself, the launch of our most ambitious space telescope. As families gathered for holiday celebrations around the world, an Ariane 5 rocket carried decades of human ingenuity and hope into the darkness above French Guiana. The timing was both practical and poetic, marking the beginning of a new era in cosmic discovery, with the most significant present we could give to future generations. Fact 6. The launch rocket was the Ariane 5. The European Ariane 5 rocket was chosen not for poetry but for precision. Its track record of successful launches made it the trusted vessel for humanity's most expensive and irreplaceable cargo. This powerful rocket had carried satellites and spacecraft for over 2 decades, building the reputation for reliability that JWST's mission demanded. On that December morning, all that accumulated trust and engineering excellence focused on a single, perfect launch into the cosmic dark. Fact 7. JWST is a collaboration between NASA, ESA, and CSA. This telescope represents something beautiful about human nature. When we reach for the stars, national boundaries seem to fade. The American NASA, European Space Agency, and Canadian Space Agency pooled their expertise, resources, and dreams to create something no single nation could achieve alone. Every golden mirror segment reflects not just starlight, but the collaborative spirit that makes our greatest achievements possible. Fact 8. JWST is often called the successor to Hubble. While Hubble revolutionized our view of the visible universe, JWST extends our gaze into the infrared realm where the universe's earliest secrets hide. It's not replacing Hubble so much as completing the picture, where Hubble showed us the universe in glorious visible detail. JWST reveals the hidden thermal landscape of cosmic evolution. Together, they give us binocular vision for the cosmos, depth perception for the universe itself. Fact 9. Its design began in the 1990s. The 1990s seem recent until you realize that some of the engineers who began designing JWST have since retired, and that college students who worked on early concepts are now leading the mission. When JWST's design began, the World Wide Web was still a novelty. Cell phones were bricks, and the idea of carrying the internet in your pocket was science fiction. Yet even then, visionaries were sketching plans for a space telescope that would see deeper than ever before. This telescope represents a generational effort, a project that spanned entire careers and outlasted multiple presidential administrations, bridging the analog and digital ages. It's a reminder that our greatest achievements often require patience measured in decades rather than years, faith that future technology will solve problems we can't yet imagine. Fact 10. JWST cost over $10 billion to build. $10 billion represents more than the GDP of many nations, all focused on a single, shining goal: to see deeper into space and time than humanity has ever managed. To put this in perspective, it's comparable to building several aircraft carriers, or funding a major university for decades, or providing clean water to millions. Yet, we chose to invest it in cosmic knowledge. That investment reflects not just the complexity of the engineering challenge, but our species' remarkable willingness to spend extraordinary sums to satisfy our cosmic curiosity. Some might question spending so much on what seems abstract, but every dollar brought precision measured in nanometers and discoveries that will reshape our understanding of the universe for generations to come. Fact 11. It took more than 20 years to complete. 20 years of human effort crystallized into this single perfect instrument floating in the cosmic dark. Think of all the birthdays, graduations, marriages, and life changes that occurred while engineers and scientists devoted their careers to making JWST possible. 2 decades of human dedication compressed into a telescope that will peer 20 billion years into the past, a machine that transforms human persistence into cosmic time travel. Fact 12. More than 10,000 people worked on it. Imagine a small city's worth of engineers, scientists, technicians and visionaries all focused on a single goal: building humanity's most sophisticated eye on the universe. These 10,000 people represent countless hours of problem-solving, innovation and dedication, each person contributing their expertise to create something far greater than any individual could achieve. Their collective brilliance now sits in space, gathering ancient starlight for all of humanity. Fact 13. Its mission is expected to last 10 years. A decade of cosmic observation awaits us, 10 years of discoveries that will likely revolutionize our understanding of galaxy formation, stellar birth, and planetary systems. Yet this 10-year expectation feels both generous and heartbreakingly brief when measured against the telescope's journey to completion. Consider the mathematics of effort versus operation. 20 years of human dedication to build something that might work for only 10 years. It's like spending 2 decades crafting a perfect musical instrument for a single transcendent concert. The disproportion seems almost tragic until you realize that those 10 years of observation will yield insights that outlast the telescope itself, knowledge that becomes part of human understanding forever. Fact 14. It could last longer if fuel runs efficiently. The possibility of extended operation beyond 10 years adds hope to the mission timeline. Like a careful driver conserving fuel for a long journey, mission controllers guide JWST with precision that could stretch its operational life well beyond the planned decade. Every efficient maneuver, every carefully calculated course correction, potentially buys us additional years of cosmic discovery, extending humanity's vision deeper into the ancient universe. Fact 15. JWST's gold-coated mirrors give it its famous look. The gleaming gold that makes JWST instantly recognizable isn't just beautiful, it's functional art that maximizes infrared reflection. Gold's unique properties make it the perfect coating for mirrors designed to see the universe's thermal glow. That distinctive golden appearance has become iconic, a visual symbol of humanity's technological artistry and our determination to see the cosmos in ways our eyes never could. Fact 16. The telescope's diameter is about the size of a house. When fully deployed, JWST spreads across space like a small house floating in the cosmic void. This domestic comparison helps us grasp the scale of what we've accomplished. We've essentially built a house-sized precision instrument and launched it into perfect darkness, where it unfolds like an origami palace designed to catch ancient light. The familiar scale makes the achievement both more relatable and more remarkable. Fact 17. JWST can see light that's over 13 billion years old. 13 billion years ago, the universe was young, hot, and filled with the first galaxies beginning to shine. The light JWST captures began its journey when our cosmos was barely 1 billion years old, traveling through expanding space, while Earth was still a dream in a nebula not yet born. Think about what this means. Every photon hitting JWST's mirrors is older than our solar system, older than the sun, older than the heavy elements that make up our planet. These ancient messengers have been traveling since before complex matter as we know it existed, crossing a universe that has expanded dramatically during their journey. When we look at JWST's images, we're not just seeing distant objects. We're seeing the actual past, preserved in light, that has travelled longer than worlds have existed. Fact 18. It studies the first galaxies after the Big Bang. JWST peers back toward the cosmic beginning, seeking the earliest galaxies that emerged from the universe's dark age. These primordial stellar cities formed when the cosmos was still learning how to make stars, when the first heavy elements were being forged in stellar cores. By studying these ancient galaxies, we're essentially reading the universe's baby pictures, understanding how cosmic structure grew from the smooth aftermath of the Big Bang. Fact 19. It also studies exoplanets and their atmospheres. Beyond cosmic archaeology, JWST serves as a planetary detective, analyzing the atmospheres of distant worlds for chemical signatures that might indicate habitability or even life itself. The same infrared sensitivity that reveals ancient galaxies can also detect water vapor, methane, and other molecules in the thin envelopes of air surrounding planets orbiting other stars. Each atmospheric analysis brings us closer to answering the profound question of whether we're alone. Fact 20. JWST is operated by the Space Telescope Science Institute in Baltimore. From a building in Baltimore, scientists and engineers command humanity's most sophisticated cosmic observatory, sending instructions across 1.5 million kilometers of space to our golden-eyed sentinel at L2. There's something wonderfully ordinary about this arrangement. In a city known for crab cakes and baseball, in an office building that could house any corporation, people sit at computers and control an instrument that peers to the edge of the observable universe. The contrast is beautiful. Morning coffee and commuter traffic below, while upstairs technicians download data from the cosmic dawn. This earthbound control center represents the vital connection between human curiosity and cosmic discovery, where data from the edge of the observable universe arrives to be transformed into images and insights that reshape our understanding of everything. Fact 21. JWST was supposed to launch in 2007. The year 2007 feels like a different era in human technology and culture, before smartphones transformed our daily lives, before social media reshaped human connection, before streaming services changed how we consume entertainment. In that simpler time, JWST was scheduled to begin its cosmic mission, a timeline that seems almost quaint in retrospect. The original plan called for a much smaller, less ambitious telescope that would have given us remarkable discoveries, but nothing approaching the revolutionary instrument we eventually built. Sometimes the universe conspires to make our greatest achievements even greater through the apparent setback of delay. Fact 22. The mission was delayed 14 years. 14 years of delays sound like failure until you realize what those years accomplished, transforming a good telescope into humanity's most sophisticated cosmic observatory. Each year of delay brought new technologies, refined engineering, and expanded capabilities that the original 2007 design never imagined. Those 14 years saw the rise of advanced computing, materials science breakthroughs, and precision manufacturing techniques that made JWST's final form possible. In cosmic terms, 14 years is barely a blink, but in human technological development, it represents several generations of innovation compressed into a single perfect instrument. Fact 23. Each delay added millions to the cost. The mounting costs of delay tell a story of human ambition wrestling with the practical limits of engineering and politics. Every year that passed brought new challenges: inflation, changing requirements, technological upgrades that made previous work obsolete, and the simple reality that keeping thousands of brilliant people employed on a single project costs enormous sums. Yet those millions bought something priceless: the time needed to get everything exactly right. In retrospect, every dollar spent on delays was an investment in perfection, ensuring that when JWST finally launched, it would work flawlessly on the first try, with no possibility of repair. Fact 24. The launch site was in French Guiana. From the edge of the Amazon rainforest, humanity launched its most sophisticated cosmic eye into the darkness above. French Guiana's location near the equator provides a natural boost from Earth's rotation, helping rockets carry their precious cargo towards space with maximum efficiency. The contrast is striking: ancient rainforest below, infinite cosmos above and in between, the product of human ingenuity beginning its journey to the edge of the solar system. This remote location has witnessed dozens of satellite launches, but none carried the weight of human dreams quite like JWST's departure on that Christmas morning. Fact 25. JWST folded up to fit inside the rocket. Imagine the most complex piece of origami ever conceived, but instead of paper, it's made from gold-coated mirrors, delicate instruments, and a sunshield the size of a tennis court. The engineering challenge of folding JWST for launch rivals anything humans have ever attempted. Every fold had to be perfect, every mechanism tested thousands of times, every deployment sequence verified through computer simulation and physical testing. The telescope essentially had to transform itself from a compact package small enough for a rocket into a house-sized precision instrument in the vacuum of space, all without human hands to guide the process. Fact 26. It took about 30 days to fully unfold. 30 days of careful, methodical deployment, each step monitored by teams of engineers who had spent decades planning every movement. Picture the tension in mission control as JWST slowly revealed itself in space, mirrors unfolding like metallic flower petals, the sunshield stretching across the cosmic void, instruments powering up for the first time in the environment they were designed for. Every day brought new milestones, new successes, and the gradual transformation of a folded package into humanity's most sophisticated cosmic observatory. Fact 27. The unfolding was called the 29 Days of Terror. This dramatic name captures the anxiety that gripped the astronomical community as JWST deployed itself in space. Unlike Earth-based projects where problems can be fixed with human hands and spare parts, every mechanism had to work perfectly on the first try, millions of kilometers from any possibility of repair. Engineers called it terror because they knew that 2 decades of work, $10 billion of investment, and humanity's cosmic ambitions all hung in the balance of mechanisms that had never been tested in the actual environment where they needed to function. The terror were justified, and thankfully unnecessary. Fact 28. Over 300 points of failure could have doomed the mission. 300 ways the mission could have ended before it truly began, a sobering reminder of how complex JWST really is. Each potential failure point represents a mechanism, motor, deployment sequence, or critical system that absolutely had to work perfectly in space. Engineers identified every possible weakness, tested every component beyond its design limits, and built redundancy wherever possible. Yet even with all that preparation, 300 potential failure points meant 300 opportunities for heartbreak, 300 reasons to hold your breath during those crucial deployment weeks. Fact 29. Its mirrors were folded like origami. The 18 hexagonal segments that formed JWST's primary mirror had to fold like the petals of a mechanical flower, each one precisely positioned to fit within the rocket's payload fairing. This wasn't simple folding, Each mirror had to maintain perfect optical alignment while being compressed, launched exposed to space, and then deployed into exactly the right position to form a single perfect reflecting surface. The origami comparison captures both the artistry and precision required, transforming functional engineering into something approaching cosmic poetry. Fact 30. Its sunshield was folded 12 times. 12 careful folds compressed a tennis court-sized sunshield into a package that could fit inside a rocket, each fold designed with the precision of master tailors working on cosmic scales. The sunshield consists of 5 layers of material thinner than human hair, yet each layer had to deploy perfectly in sequence, stretching tight across its frame like a vast metallic sail. Those 12 folds had to unfold in exactly the right order, at exactly the right time, to create the thermal barrier that keeps JWST's instruments cold enough to detect the faintest infrared signals from the edge of the universe. Fact 31. The sunshield had to unfold perfectly. Perfect deployment wasn't just desirable, it was absolutely essential for mission success. Any wrinkle, tear, or misalignment in the sunshield would compromise JWST's ability to maintain the ultra-cold temperatures its infrared instruments require. The shield acts like a cosmic umbrella, blocking the sun's heat while allowing the telescope to cool to nearly absolute zero. There were no second chances, no backup plans, no possibility of smoothing out wrinkles by hand. The sunshield had to unfold perfectly on the first try, and remarkably, it did exactly that. Fact 32. The telescope travelled about 1.5 million kilometres to its orbit. 1.5 million kilometres represents a journey far beyond the comfortable realm of near-Earth space, into a region where the gravitational influences of Earth and Sun create a stable parking spot for cosmic observation. This distance is so vast that light from JWST takes several seconds to reach Earth, making real-time control impossible. Every command sent to the telescope has to account for this delay, and every response takes precious seconds to return. It's humanity's most distant outpost, our furthest functioning embassy in the cosmic dark. Fact 33. That's 4 times farther than the Moon. Using the Moon as a reference point helps us grasp the enormity of JWST's journey. It travelled 4 times further than the furthest humans have ever ventured from Earth. While Apollo astronauts look back at Earth from lunar distance, JWST gazes at our world from a vantage point that makes Earth and Moon appear as close neighbours. From JWST's perspective, our entire Earth-Moon system occupies just a tiny patch of sky, a humbling reminder of how far our most sophisticated instruments must travel to escape the thermal interference of our local cosmic environment. Fact 34. JWST reached orbit in January 2022. After its Christmas Day launch, JWST spent a month travelling through space, gradually moving away from Earth's gravitational embrace toward its final destination. January 2022 marked the end of one journey and the beginning of another. The physical journey complete, the scientific mission just beginning. Reaching L2 was like arriving at a cosmic research station, a perfect vantage point for observing the universe without interference from Earth's heat or the Moon's gravitational perturbations. Fact 35. The Ariane 5 rocket was chosen for its reliability. Reliability becomes paramount when your cargo is irreplaceable and worth $10 billion. The Ariane 5 had demonstrated its trustworthiness through decades of successful launches, carrying satellites and space missions with a track record that inspired confidence. Choosing a rocket isn't just about power, it's about trust, about finding a launch vehicle with the proven ability to deliver precious cargo safely to space. The Ariane 5's reputation was built on dozens of previous successes, each one contributing to the confidence that it could safely carry humanity's most valuable scientific instrument beyond Earth's atmosphere. Fact 36. JWST launched without any major problems. After decades of preparation, years of delays, and months of final checks, the actual launch proceeded with almost boring perfection. No dramatic last-minute issues, no heart-stopping mechanical failures, no weather delays, just a smooth, routine ascent that belied the enormity of what was happening. Sometimes the most important moments in human history unfold with quiet efficiency rather than dramatic spectacle. The lack of problems was itself a testament to the extraordinary preparation that had gone into every aspect of the mission. Fact 37. The final cost included both the telescope and launch. The $10 billion price tag encompasses not just the telescope itself, but the rocket that carried it to space, the ground operations that guide it, and the decades of human effort that made it possible. Breaking down the cost reveals investments in materials science, precision manufacturing, computer modeling, testing facilities, and the salaries of thousands of brilliant people working toward a single goal. Every component of that cost represents human knowledge being pushed to its limits, technology being refined to unprecedented precision, and our species' determination to see deeper into the cosmos than ever before. Fact 38. The telescope weighs about 6.2 tons. 6.5 tons might seem modest for humanity's most sophisticated space telescope, until you realize that every gram had to be justified, every component optimized for the harsh environment of space. This weight represents the careful balance between capability and launchability, heavy enough to house the complex instruments needed for cosmic observation, light enough to be carried beyond Earth's gravitational well. Those 6.2 tons include some of the most precisely manufactured materials ever created, from gold-coated beryllium mirrors to instruments cooled to nearly absolute zero. Fact 39. The journey to orbit took about a month. A month of careful navigation through space, with course corrections and trajectory adjustments, guided by mission controllers watching from Earth. Unlike the dramatic acceleration of launch, the journey to L2 was a gradual cruise through increasingly empty space, each day taking JWST further from Earth's influence and closer to its final observing position. That month represented a transition period, no longer Earth-bound, not yet fully operational, but steadily approaching the moment when humanity's most sophisticated eye would open onto the cosmos. Fact 40. Once in place, it cooled down to operating temperature. Reaching L2 was only the beginning. JWST then had to cool down to the ultra-cold temperatures required for infrared observation. Like a camera adjusting to darkness, the telescope gradually shed the warmth of Earth and the residual heat of launch, its instruments slowly reaching the temperature of deep space itself. This cooling process took months as heat gradually radiated away into the cosmic void, transforming JWST from a warm, Earth-launched machine into a cold, space-adapted instrument ready to detect the faintest thermal whispers from the edge of the observable universe. Fact 41. JWST orbits around the L2 point. L2, or Lagrange point 2, represents one of those elegant solutions that nature provides when gravity and orbital mechanics align perfectly. This invisible point in space exists where Earth's gravity and the Sun's gravity balance in such a way that an object placed there will orbit the Sun at exactly the same rate as Earth, maintaining a constant position relative to our planet. It's like finding a cosmic parking spot that moves with Earth as we journey around the Sun, a gravitational sweet spot that allows JWST to maintain its position without constant fuel-burning adjustments. The mathematics that govern L2 were worked out centuries ago, but only now do we have the technology to place our most sophisticated instruments in these cosmic harbours. Fact 42. L2 is a gravitational sweet spot. Imagine balancing a pencil on your finger, that delicate equilibrium where opposing forces create perfect stability. L2 works on similar principles but with the massive gravitational fields of Earth and Sun doing the balancing. This point in space represents a solution to the three-body problem, one of physics' classic challenges involving the gravitational interactions between multiple objects. At L2, JWST can maintain its position relative to Earth with minimal fuel expenditure, like a cosmic surfer riding the gravitational waves created by our planet's orbital motion. This elegant positioning allows the telescope to observe deep space continuously without Earth ever blocking its view of the universe. Fact 43. L2 is always opposite the Sun. The geometry of L2 creates a perpetual cosmic alignment. As Earth orbits the Sun, L2 moves with it, always maintaining its position on the nighttime side of our planet. This means JWST permanently faces away from our solar system's brightest heat source, crucial for maintaining the ultra-cold temperatures its infrared instruments require. It's like having a cosmic umbrella that never needs adjustment, a position that naturally shields the telescope from solar interference while providing an unobstructed view of the universe beyond. This positioning represents millions of years of celestial mechanics compressed into a perfect observing platform. Fact 44. It's 1.5 million kilometers from Earth. 1.5 million kilometers stretches beyond comfortable human comprehension, roughly 4 times the distance to the Moon, farther than any human has ever travelled from Earth. At this distance, our planet appears as just another point of light in the cosmic darkness, no longer the overwhelmingly dominant feature it seems from low Earth orbit. JWST exists in a realm where Earth's influence becomes subtle rather than overwhelming, where the spacecraft must function autonomously for long periods, because radio signals take several seconds to cross the void between mission control and telescope. This distance represents humanity's furthest permanent outpost, our most distant functioning embassy in the cosmos. Fact 45. That's 1,000 times farther than Hubble. Hubble orbits just a few hundred kilometers above Earth's surface, close enough that astronauts can visit for repairs and upgrades, near enough that Earth fills much of the sky when viewed from the telescope. JWST, by contrast, operates in a realm of cosmic isolation where Earth appears as a distant blue dot, where repair missions are impossible, and where the spacecraft must function perfectly for years without human intervention. This 1,000-fold increase in distance represents not just a change in location, but a fundamental shift in how we design and operate space telescopes, from serviceable instruments to self-sufficient cosmic observatories. Fact 46. It takes about 6 months to travel there. 6 months represents a leisurely cosmic cruise compared to the dramatic acceleration of launch day. The journey to L2 follows a carefully calculated trajectory that takes advantage of gravitational assists and fuel-efficient paths through space. Unlike the urgent escape from Earth's gravity well, the trip to L2 allows for course corrections, system checks, and gradual deployment of the telescope's complex mechanisms. Those months of travel serve as a shakedown cruise, testing systems in the space environment while slowly approaching the telescope's final operating position. It's a journey that transforms a folded, Earth-launched package into a fully deployed cosmic observatory. Fact 47. JWST orbits L2 every 6 months. Even at the gravitational balance point of L2, JWST doesn't simply sit stationary. It follows a graceful halo orbit around this invisible point in space, completing one loop every 6 months. This orbital motion prevents the spacecraft from drifting away from L2 while providing slightly different perspectives on the cosmos throughout the year. The orbit itself is an elegant dance choreographed by celestial mechanics, allowing JWST to maintain its position relative to Earth and Sun, while slowly cycling through different orientations that optimize its observing opportunities. It's like a cosmic figure skater performing an endless, precise routine in the gravitational arena of the solar system. Fact 48. The orbit keeps its instruments cold. The halo orbit around L2 serves multiple purposes, but perhaps none more crucial than thermal management. By maintaining its position in Earth's shadow relative to the Sun, JWST can keep its instruments at the ultra-cold temperatures required for infrared astronomy. The orbit ensures that the telescope never strays into direct sunlight, never experiences the thermal chaos that would result from varying solar heating. This cosmic refrigeration system allows JWST's instruments to operate at temperatures colder than the surface of Pluto, cold enough to detect the faintest thermal whispers from the most distant galaxies in the observable universe. Fact 49. JWST always faces away from the Sun. This permanent orientation creates a cosmic version of perpetual midnight for JWST's instruments. Like a flower that always faces away from the Sun, the telescope maintains its orientation through careful positioning and the natural dynamics of its L2 orbit. This consistent shadowing is essential for infrared astronomy. Any exposure to direct sunlight would flood the sensitive detectors with thermal noise, making it impossible to detect the faint heat signatures of distant cosmic objects. The telescope's permanent back-to-the-sun posture represents one of the key engineering solutions that makes JWST's revolutionary observations possible. Fact 50. Its sunshield blocks heat and light. The sunshield functions as both umbrella and radiator, a 5-layer barrier that creates one of the most dramatic temperature differences in the solar system. On the sun-facing side, temperatures reach a toasty 85 degrees Celsius, hot enough to boil water if any existed there. Meanwhile, just a few meters away on the shadowed side, temperatures plummet to minus 233 degrees Celsius, colder than the surface of Neptune. This thermal barrier makes JWST's observations possible by creating an island of cosmic cold in the relatively warm environment of the inner solar system, allowing infrared instruments to function with unprecedented sensitivity. Fact 51. The sunshield is the size of a tennis court. Picture a tennis court floating in space, made from materials thinner than human hair, yet capable of blocking the tremendous thermal output of our nearest star. This vast metallic sail stretches across the cosmic void, creating a shadow zone where JWST's delicate instruments can operate at temperatures approaching absolute zero. The scale is breathtaking, a tennis court's worth of precisely engineered material deployed with origami-like precision in the vacuum of space, all to create the thermal conditions necessary for peering into the infrared glow of the early universe. Every square meter of that sunshield contributes to humanity's ability to see deeper into space and time than ever before. Fact 52. It has 5 protective layers. 5 separate layers work together like a cosmic Russian doll, each one contributing to the overall thermal protection that makes JWST's mission possible. These layers create multiple barriers against solar radiation, with each successive layer becoming progressively cooler as heat is reflected and radiated away into space. The multi-layer design provides redundancy. If one layer were damaged by micrometeoroids or other space debris, the remaining layers would continue to provide essential thermal protection. Together, these 5 gossamer-thin barriers create one of the most effective thermal shields ever deployed in space. Fact 53. Each layer is thinner than a human hair. The engineering achievement of creating tennis court-sized barriers from material thinner than human hair borders on the miraculous. These ultra-thin layers must maintain their integrity in the harsh environment of space while providing crucial thermal protection for the telescope's instruments. The thinness isn't just impressive, it's functional, allowing the layers to be folded for launch, while remaining strong enough to deploy and maintain tension in space. Working with materials this delicate requires manufacturing precision that pushes the boundaries of what's possible with current technology. Fact 54. The shield reduces heat by a factor of 1,000,000. A 1,000,000-fold reduction in thermal energy represents one of the most dramatic environmental transitions created by human engineering. The sunshield transforms the environment from the relatively warm inner solar system to conditions approaching the cosmic background temperature. The residual heat left over from the Big Bang itself. This 1,000,000-fold reduction allows JWST to detect infrared radiation from objects so distant and faint that their thermal signatures would be completely overwhelmed without this extraordinary level of thermal isolation. It's like creating a bubble of intergalactic space within our own solar system. Fact 55. The hot side of the shield is approximately 85 degrees Celsius. 85 degrees Celsius on the sun-facing side of the sunshield, hot enough to brew tea if you could somehow transport a kettle to L2. This temperature reflects the intensity of solar radiation even at Earth's distance from the sun, demonstrating why thermal protection is so crucial for sensitive astronomical instruments. The hot side of the sunshield absorbs and radiates this solar energy, preventing it from reaching the telescope's delicate infrared detectors. That 85-degree temperature represents the sacrifice the sunshield makes, taking the solar punishment so JWST's instruments can observe in cosmic tranquility. Fact 56. The cold side is approximately minus 233 degrees Celsius. Negative 233 degrees Celsius represents a temperature so cold it challenges human intuition, colder than the surface of any planet in our solar system, approaching the fundamental limit of how cold matter can become. At this temperature, most gases would freeze solid, and even the motion of atoms slows to a crawl. This extreme cold is exactly what JWST's infrared instruments need to detect the faintest thermal radiation from the most distant objects in the universe. The cold side of the sunshield creates an environment more frigid than the space between galaxies, all in service of humanity's cosmic curiosity. Fact 57. The telescope itself operates near absolute zero. Operating near absolute zero means JWST's instruments function at temperatures where the fundamental behavior of matter changes, where thermal noise drops to levels that allow detection of the faintest cosmic signals. Absolute zero represents the theoretical limit, where all atomic motion stops. JWST operates just a few degrees above this ultimate cold, in a thermal environment more extreme than anything found naturally in our solar system. This extreme cooling transforms the telescope into an incredibly sensitive thermometer for the universe, capable of detecting temperature differences across cosmic distances. Fact 58. Its location prevents astronauts from repairing it. The 1.5 million kilometre distance to L2 places JWST far beyond the reach of human repair missions, creating both vulnerability and independence. Unlike Hubble, which has benefited from multiple astronaut servicing missions, JWST must function perfectly from the moment of deployment until the end of its mission. This distance forces a different design philosophy. Everything must work correctly the first time, with redundant systems and careful engineering replacing the possibility of human intervention. The isolation is both sobering and liberating, freeing JWST from the constraints of human accessibility while demanding unprecedented reliability. Fact 59. Hubble could be serviced. JWST cannot. The contrast between serviceable and autonomous represents a fundamental shift in space telescope design philosophy. Hubble's location in low Earth orbit made it accessible to astronauts who could replace components, upgrade instruments, and fix problems that would have ended the mission. JWST's distant location demands a different approach: perfect engineering from the start, redundant systems throughout, and the acceptance that any critical failure would end the mission. This constraint drove engineers to achieve levels of reliability and precision that exceed anything previously attempted in space-based astronomy. Fact 60. JWST will eventually drift after its mission ends. When JWST's fuel finally runs out and its mission concludes, the telescope will begin a slow drift away from L2, eventually becoming a derelict monument to human achievement, wandering through interplanetary space. Unlike Earth-orbiting satellites that eventually fall back to our planet, JWST will continue its journey through the solar system, carrying with it the golden mirrors and sophisticated instruments that revolutionized our understanding of the cosmos. Millions of years from now, this silent ambassador of human curiosity will still be traveling through space, a technological fossil from the era when humanity first learned to see the infrared universe with unprecedented clarity. Fact 61. JWST's main mirror has 18 segments. 18 hexagonal segments work together as one perfect surface, each piece precisely shaped and positioned to create humanity's largest space-based mirror. This segmented design wasn't chosen for aesthetics. It was the only way to fit a 6.5-meter mirror inside a rocket fairing designed for much smaller payloads. Each segment is a masterpiece of optical engineering, ground and polished to tolerances measured in nanometers, then coated with gold to optimize infrared reflection. Together, these 18 pieces form a honeycomb pattern that maximizes collecting area while maintaining the structural integrity needed to survive launch and deployment. The segmented approach represents a triumph of engineering compromise, achieving the impossible by breaking it into manageable pieces. Fact 62. Each segment is made of beryllium. Beryllium was chosen for JWST's mirrors, not because it's common, it's actually quite rare and toxic to work with, but because it possesses a unique combination of properties essential for space-based astronomy. This lightweight metal maintains its shape across the extreme temperature variations of space, from the warmth of Earth's vicinity to the cosmic cold of L2. Beryllium's thermal stability means the mirrors won't warp as the telescope cools down, maintaining their precise optical shapes even as temperatures drop hundreds of degrees. Working with beryllium requires extraordinary safety precautions due to its toxicity, but the metal's properties make it irreplaceable for applications demanding both lightness and dimensional stability in harsh environments. Fact 63. The mirrors are coated in gold. Gold coating transforms each beryllium mirror segment into a precise reflector optimized for infrared light, the wavelengths that carry the most information about the early universe and distant cosmic objects. Gold was chosen not for its beauty, though the result is undeniably striking, but for its superior infrared reflectivity and resistance to corrosion in space. Unlike silver, which tarnishes and degrades over time, gold maintains its optical properties indefinitely, ensuring that JWST's mirrors will perform consistently throughout the mission's duration. The golden surface creates the telescope's iconic appearance, while serving the practical purpose of bouncing infrared photons toward the instruments with maximum efficiency. Fact 64. The gold layer is only 100 nanometers thick. 100 nanometers, a coating so thin it's measured in billionths of a meter, thinner than a soap bubble, yet crucial for JWST's ability to observe the infrared universe. This incredibly thin layer demonstrates the precision of modern manufacturing techniques, applying gold with atomic-level control to create perfectly uniform optical surfaces. Despite its thinness, this coating will endure the harsh environment of space for decades, maintaining its reflective properties while exposed to cosmic radiation, micrometeoroid impacts, and extreme temperature variations. The achievement of applying such thin, uniform coatings across mirror segments, the size of conference tables, represents a triumph of materials science and precision manufacturing. Fact 65. That's less than 1/10,000th for the thickness of a sheet of paper. To grasp how thin 100 nanometers really is, imagine taking a standard sheet of paper and slicing it into 10,000 layers. Each layer would be roughly the thickness of JWST's gold coating. This comparison helps us appreciate the extraordinary precision required to manufacture the telescope's mirrors, where tolerances are measured in dimensions smaller than the wavelength of visible light. Working at this scale requires techniques borrowed from the semiconductor industry, where engineers routinely manipulate matter at the atomic level. The fact that such impossibly thin coatings can be applied uniformly across large mirror segments speaks to humanity's mastery of material science at the nanoscale. Fact 66. The total gold weighs about 48 grams. 48 grams of gold, roughly the weight of a standard golf ball, provides the reflective coating for humanity's largest space telescope. This modest amount of precious metal, distributed across 25 square meters of mirror surface, enables observations that span billions of light years. The total gold content is worth less than the cost of a decent laptop, yet its application with nanometer precision makes it invaluable for cosmic discovery. This demonstrates how advanced manufacturing can transform small amounts of material into revolutionary capabilities, where the value lies not in the raw materials, but in the precision with which they're applied. Fact 67. That's about the weight of a golf ball. A golf ball's worth of gold, spread atom-thin across mirrors larger than dining room tables, captures the essence of JWST's engineering philosophy, achieving maximum capability with minimum mass. Space missions operate under strict weight limits, where every gram must justify its inclusion, and JWST's designers found ways to maximize performance while minimizing mass. The golf ball comparison makes the achievement tangible. Such a small amount of material enabling such profound discoveries. It's a reminder that in precision engineering, it's not how much material you use, but how cleverly you use what you have. Fact 68. The mirrors can adjust themselves in space. Each of JWST's 18 mirror segments can move and reshape itself in space, fine-tuning the telescope's focus with precision that borders on the magical. This active adjustment capability allows the segmented mirror to function as a single, perfect optical surface, despite being composed of separate pieces that experience the stresses of launch and the thermal changes of space travel. The mirrors can adjust their positions by distances smaller than the width of a virus, compensating for tiny imperfections and ensuring that starlight from across the universe focuses to perfect points on the telescope's detectors. This self-adjusting capability transforms a collection of individual mirrors into a unified, precision instrument. Fact 69. Each mirror segment has tiny motors. Tiny actuators behind each mirror segment provide the mechanical muscle for these nanometer-scale adjustments. Motors so precise they can move mirror segments by distances smaller than the wavelength of light itself. These motors represent a miniaturized version of the technology that positions Earth-based telescope mirrors, shrunk down and hardened for the space environment. Each actuator must function reliably for years in the harsh conditions of space, maintaining its precision despite cosmic radiation, extreme temperatures, and the complete absence of maintenance. The motors enable JWST to maintain perfect focus throughout its mission, compensating for thermal changes and mechanical settling that would otherwise degrade image quality. Fact 70. The telescope has 4 main instruments. 4 sophisticated instruments transform the ancient photons collected by JWST's golden mirrors into the scientific data that revolutionizes our understanding of the universe. Each instrument represents a specialized detector optimized for different aspects of infrared astronomy, from capturing detailed images of distant galaxies to analyzing the chemical composition of exoplanet atmospheres. Together, these 4 instruments give JWST the versatility to tackle multiple scientific objectives, from studying the formation of the first stars to searching for signs of life on distant worlds. The quartet of instruments represents years of development by teams of scientists and engineers, each contributing unique capabilities to humanity's cosmic investigation toolkit. Fact 71. NIRCam captures near-infrared images. The near-infrared camera serves as JWST's primary imager, capturing detailed pictures of cosmic objects in wavelengths of light just beyond what human eyes can see. NIRCam's images reveal structures and details invisible to optical telescopes, showing us star formation regions shrouded in dust, the thermal glow of brown dwarfs too cool to shine in visible light, and galaxies so distant their light has been redshifted into the infrared by cosmic expansion. This instrument produces the stunning false-color images that capture public imagination, while providing astronomers with precise photometric data about cosmic objects across vast distances and time periods. Fact 72. NIRSpec splits light into spectra. Near-infrared spectrograph dissects starlight like a cosmic prism, spreading the light from distant objects into component wavelengths that reveal their chemical composition, temperature, motion, and physical conditions. Where NIRCam shows us what cosmic objects look like, NRSpec tells us what they're made of and how they behave. This instrument can analyze light from hundreds of objects simultaneously, providing detailed chemical fingerprints that reveal the presence of specific elements and molecules across cosmic distances. Spectroscopy transforms astronomy from merely observational to truly analytical, allowing us to understand the physical nature of objects we can never directly touch. Fact 73. MIRI studies mid-infrared light. The mid-infrared instrument operates at longer infrared wavelengths, detecting thermal radiation from warm cosmic objects and revealing phenomena invisible to other instruments. MIRI requires the coldest operating temperatures of any JWST instrument, functioning at just a few degrees above absolute zero to minimize thermal noise that would overwhelm the faint signals it's designed to detect. This instrument excels at studying the warm dust around forming stars, the thermal emission from exoplanet atmospheres, and the complex organic molecules that might indicate biological processes on distant worlds. MIRI extends JWST's sensitivity into wavelength regions where the universe reveals its warmest secrets. Fact 74. FGS/NIRISS helps with alignment and exoplanet studies. The Fine Guidance Sensor and Near-Infrared Imager and slitless spectrograph serves the dual purpose of keeping JWST precisely pointed while conducting specialized observations of exoplanets and other cosmic objects. The guidance function ensures that the telescope maintains its pointing accuracy to within milliarc seconds, steady enough to keep distant stars perfectly centered on detectors throughout long observations. Meanwhile, NIRISS excels at detecting and analyzing exoplanet atmospheres, particularly during planetary transits, when these distant worlds pass in front of their host stars. This dual-purpose instrument demonstrates the efficiency required for space missions, where every component must earn its place through multiple contributions to the overall mission. Fact 75. Its detectors are sensitive to faint heat signals. JWST's detectors can sense thermal radiation so faint it would be like detecting the heat from a candle on the moon, if such detection were possible across the vacuum of space. These incredibly sensitive instruments operate at temperatures approaching absolute zero, where their own thermal noise drops to levels that allow detection of the faintest cosmic signals. The detectors use advanced semiconductor technology to convert individual infrared photons into electrical signals, preserving the information carried by light that has traveled billions of years to reach us. This extraordinary sensitivity enables JWST to observe objects so distant and faint they represent the universe in its infancy. Fact 76. It sends data back to Earth every day. Every day, JWST transmits its cosmic discoveries across 1.5 million kilometers of space, beaming precious observations back to eager astronomers on Earth. This daily data dump contains images and spectra that might reveal new galaxies, unexpected atmospheric compositions of exoplanets, or evidence of the universe's earliest star formation. The regular data transmission creates a constant stream of discovery, with new observations arriving daily to be processed, analyzed, and shared with the global scientific community. Each daily transmission might contain the data that answers fundamental questions about cosmic evolution, stellar formation, or the possibility of life beyond Earth. Fact 77. It communicates via the Deep Space Network. The Deep Space Network, a collection of massive radio dishes scattered across Earth, serves as humanity's communication link with our most distant space missions, including JWST. These enormous antennas, located in California, Spain, and Australia, ensure that at least one dish can always communicate with spacecraft, regardless of Earth's rotation. The network represents decades of engineering refinement, creating reliable communication channels across interplanetary distances. When JWST sends its daily data transmission, these dishes capture the faint radio signals carrying cosmic discoveries, demonstrating how Earth-based infrastructure enables the success of space-based science. Fact 78. It produces about 57 gigabytes of data daily. 57 gigabytes per day represents an enormous flow of cosmic information, enough data to fill roughly 12 DVDs daily with images and spectra from the edge of the observable universe. This data stream contains the raw observations that will keep astronomers busy for decades, providing material for countless research papers, discoveries, and insights into cosmic evolution. The volume reflects JWST's incredible productivity as a scientific instrument, continuously gathering information that expands human knowledge of the universe. Managing and processing this daily flood of data requires sophisticated computer systems and analysis techniques that transform raw observations into scientific understanding. Fact 79. The telescope uses liquid helium for cooling. Liquid helium provides the ultra-cold environment that MIRI requires for optimal performance, cooling the instrument to temperatures just a few degrees above absolute zero. This exotic coolant boils at -269 degrees Celsius, creating conditions cold enough to minimize thermal noise that would otherwise overwhelm the faint infrared signals MIRI is designed to detect. The helium cooling system represents one of the most technically challenging aspects of JWST's operation, requiring sophisticated engineering to maintain these extreme temperatures in space. The liquid helium supply is finite, making it one of the limiting factors in JWST's operational lifetime. Fact 80. The MIRI instrument is the coldest part. MIRI operates at the coldest temperatures achieved by any space-based astronomical instrument, functioning in conditions approaching the fundamental limits of how cold matter can become. This extreme cooling is necessary because thermal radiation from the instrument itself would overwhelm the faint infrared signals from distant cosmic objects. At these temperatures, even the random motion of atoms slows dramatically, creating an environment quiet enough to detect heat signatures from objects billions of light-years away. The achievement of maintaining such cold temperatures in space represents a triumph of cryogenic engineering and thermal management. Fact 81. Its instruments work at around -266 degrees Celsius. -266 degrees Celsius, just 7 degrees above absolute zero, creates operating conditions more extreme than the coldest natural environment in the solar system. At these temperatures, most materials become superconductors, gases freeze into solids, and the thermal motion that creates noise in electronic systems drops to negligible levels. This extreme cold transforms JWST's instruments into incredibly sensitive thermometers for the universe, capable of detecting temperature differences across cosmic distances. The achievement of maintaining such temperatures while operating complex electronic systems represents one of the most impressive aspects of JWST's engineering. Factor 82. JWST's pointing system is extremely stable. JWST can hold its pointing steady to within milliseconds, roughly equivalent to holding a laser pointer steady on a coin from 100 kilometers away. This extraordinary stability allows the telescope to track cosmic objects precisely during long observations, essential for gathering enough photons from faint, distant targets. The pointing system uses gyroscopes, star trackers, and fine guidance sensors, working together to maintain this remarkable stability despite the spacecraft's location far from Earth. This precision enables JWST to observe the same cosmic targets for hours or days, accumulating the light needed to study the universe's faintest and most distant objects. Fact 83. It can point to targets within milliarcseconds. Milliarcsecond. Pointing accuracy represents precision that staggers the imagination, equivalent to hitting a target the size of a coin from hundreds of kilometers away. This accuracy is essential for infrared astronomy, where long exposure times are often needed to gather enough photons from faint cosmic sources. The pointing system must compensate for tiny mechanical variations, thermal effects, and the subtle gravitational influences acting on the spacecraft at L2. Achieving this level of precision required developing new technologies for space-based stabilization, creating pointing capabilities that exceed anything previously achieved in astronomical instruments. Fact 84. Its mirrors are polished to within nanometers. The surface accuracy of JWST's mirrors represents some of the most precise manufacturing ever achieved, with deviations measured in nanometers, distances smaller than the wavelength of visible light. This extraordinary smoothness ensures that infrared radiation reflects perfectly from the mirror surfaces, maintaining the phase relationships between light waves that create sharp, detailed images. Polishing mirrors to nanometer accuracy requires techniques borrowed from the semiconductor industry, where similar precision is needed for manufacturing computer chips. The achievement of creating large mirrors with such smooth surfaces demonstrates humanity's mastery of precision manufacturing at almost atomic scales. Fact 85. The telescope runs on solar power. Despite operating in the permanent shadow created by its sunshield, JWST generates electrical power using solar panels positioned to capture sunlight while keeping the instruments cold. This solar array must operate efficiently in the deep space environment, converting photons from our nearest star into the electricity that powers humanity's most sophisticated cosmic observatory. The solar panels represent a reliable, long-term power source that can operate for years without maintenance, essential for a mission located far beyond the reach of human servicing. The irony is beautiful. JWST hides from the sun's heat while simultaneously depending on solar energy to power its revolutionary observations of the infrared universe. Fact 86. JWST captured the deepest infrared image ever taken. When JWST turned its golden mirrors toward a seemingly empty patch of sky and stared for days, it created the deepest view into the infrared universe ever achieved, revealing cosmic history with unprecedented clarity. This deep-field image required pointing the telescope at the same tiny region for over 12 hours, allowing ancient photons to accumulate on the detectors like cosmic raindrops filling a bucket. The resulting image penetrates further into space and time than any previous infrared observation, showing us galaxies as they appeared when the universe was a fraction of its current age. Each photon captured in this deep exposure carried information across billions of light years, creating a time machine that reveals the cosmos in its youth. Fact 87. It revealed thousands of galaxies in one shot. In a single image spanning an area of sky smaller than a grain of sand held at arm's length, JWST revealed thousands of galaxies scattered across cosmic time, like stars scattered across the night sky. Each galaxy in this crowded field represents billions of stars, countless worlds, and eons of cosmic evolution compressed into tiny points of light. The image demonstrates the universe's incredible richness. Even the apparently emptiest regions of space teem with galaxies when observed with sufficient sensitivity. This galactic abundance speaks to the fundamental productivity of the cosmos, where matter organizes itself into island universes, wherever conditions allow stellar formation to ignite. Fact 88. Some galaxies are over 13 billion years old. 13 billion years ago, when the universe was barely 700 million years old, the galaxies in JWST's deep field images were already shining with the light of millions of newborn stars. These ancient stellar cities formed during the cosmic dawn, when the first generation of stars was beginning to forge heavy elements in their nuclear cores, and the universe was taking its first steps toward the complex chemistry that would eventually enable planets and life. Observing these primordial galaxies is like reading the universe's birth certificate, seeing cosmic structure in its infancy when everything we now take for granted was still experimental and new. Fact 89. JWST studied the Carina Nebula. The Carina Nebula, a stellar nursery located about 7,500 light-years from Earth, became one of JWST's first showcase targets, revealing star formation with detail that transforms our understanding of how cosmic creation works. This nebula represents a cosmic maternity ward where massive clouds of gas and dust collapse under their own gravity to birth new stars, some so massive they will live fast and die young in spectacular supernova explosions. JWST's infrared vision penetrates the dust that obscures these stellar birthplaces in visible light, revealing the intricate process by which the universe continues to create new suns and potentially new planetary systems. Fact 90. It showed newborn stars in stunning detail. JWST's infrared eyes reveal newborn stars still wrapped in the cosmic cocoons of gas and dust from which they formed, like cosmic infants taking their first breaths of stellar fusion. These stellar babies appear as brilliant points of light surrounded by the debris of their formation, planetary disks where worlds might eventually coalesce, jets of material ejected during the chaotic process of gravitational collapse, and shock waves that might trigger the formation of additional stars nearby. Each newborn star represents a triumph of gravity over the random motion of gas, order emerging from cosmic chaos through the fundamental forces that shape the universe. Fact 91. It revealed cosmic cliffs and star nurseries. The infrared images from JWST transform nebulae into cosmic landscapes that seem almost geographical. Towering cliffs of gas and dust carved by stellar winds, valleys where new stars are forming, and plains of space where older stars have cleared away the material of their birth. These cosmic cliffs represent the boundaries between hot, ionized gas, heated by massive stars, and cooler, denser regions where star formation continues. The landscape metaphor isn't merely poetic. These structures represent real three-dimensional geography in space, with features spanning light years and shaped by forces that dwarf anything in our earthly experience. Fact 92. JWST studied the Southern Ring Nebula. The Southern Ring Nebula became a perfect target for demonstrating JWST's ability to reveal hidden details in cosmic objects, showing a dying star's final performance in unprecedented clarity. This planetary nebula, despite its name having nothing to do with planets, represents the beautiful death throes of a star similar to our Sun, expelling its outer layers in a series of symmetric shells that create one of nature's most elegant cosmic sculptures. JWST's observations reveal the complex structure of these gas shells, the chemical composition of the expelled material, and details about the stellar death process that creates these gorgeous cosmic monuments. Fact 93. It revealed a hidden dying star. Within the Southern Ring Nebula, JWST discovered a second star that had been hidden behind dust and gas, revealing that this cosmic display results from a stellar duet rather than a solo performance. This hidden companion star helps explain the nebula's complex structure. The gravitational dance between the two stars shaped the expelled gas into the intricate patterns we observe today. The discovery demonstrates how JWST's infrared vision can penetrate cosmic dust to reveal hidden components of astronomical systems, often finding that objects we thought we understood are actually more complex and interesting than previous observations suggested. Fact 94. JWST detected water in exoplanet atmospheres. The detection of water vapor in the atmosphere of a distant exoplanet represents one of JWST's most profound achievements, identifying the presence of a molecule essential for life as we know it around a star other than our Sun. This discovery required analyzing the tiny changes in starlight as the exoplanet passed in front of its host star, with different wavelengths of infrared light being absorbed by different atmospheric components. The presence of water vapor doesn't necessarily indicate life, but it represents a crucial prerequisite for biology as we understand it, bringing us one step closer to answering the profound question of whether we're alone in the universe. Fact 95. It also detected carbon dioxide. Carbon dioxide detection in exoplanet atmospheres adds another piece to the puzzle of understanding worlds beyond our solar system, revealing the chemical complexity that exists around other stars. This molecule provides insights into planetary formation, atmospheric evolution, and the chemical processes that shape distant worlds. The ability to detect specific molecules across interstellar distances demonstrates the extraordinary sensitivity of JWST's instruments, distinguishing the spectral fingerprints of individual chemical compounds in the thin atmospheric shells surrounding planets many light years away. Each molecular detection expands our understanding of planetary diversity and the range of environments that might exist throughout the galaxy. Fact 96. It studied the exoplanet WASP-39b. WASP-39b became one of JWST's first exoplanet targets, a hot Jupiter orbiting very close to its host star, providing an ideal laboratory for testing the telescope's atmospheric analysis capabilities. This planet, roughly the mass of Saturn but orbiting much closer to its star than Mercury orbits our Sun, experiences extreme temperatures that create dynamic atmospheric conditions perfect for spectroscopic study. JWST's observations of WASP-39b reveal detailed atmospheric composition, temperature structure, and chemical processes, demonstrating the telescope's ability to characterize exoplanet atmospheres with unprecedented precision and establishing techniques that can be applied to potentially habitable worlds. Fact 97. JWST confirmed atmospheric chemistry models. The detailed atmospheric observations of exoplanets have validated theoretical models of planetary atmosphere formation and evolution, providing crucial confirmation that our understanding of these distant worlds rests on solid scientific foundations. These confirmations are important because they give astronomers confidence in applying similar models to planets we can't observe as easily, smaller, potentially habitable worlds where the atmospheric signals are much fainter. When JWST's observations match theoretical predictions, it validates decades of computational modeling and provides confidence for extending those models to explore the atmospheric possibilities of Earth-sized planets in the habitable zones of their host stars. Fact 98. It found galaxies that appear too old for current models. Some of the most distant galaxies observed by JWST appear surprisingly mature and massive for their cosmic age, challenging our understanding of how quickly galaxies can form and evolve in the early universe. These ancient stellar cities seem to have assembled their billions of stars faster than current models predict, suggesting that galaxy formation in the early universe proceeded more rapidly or efficiently than astronomers previously believed. These observations force scientists to reconsider the timeline of cosmic evolution, potentially requiring modifications to our understanding of how matter organized itself into the large-scale structures we observe today. Fact 99. These early galaxies challenged theories of formation. The unexpected maturity of early galaxies revealed by JWST suggests that the universe became organized and productive much earlier than previously thought, compressing billions of years of expected evolution into a much shorter time frame. These observations challenge fundamental assumptions about how quickly stars can form, how efficiently gas can be converted into stellar mass, and how rapidly galaxies can assemble from the cosmic web of dark matter. The discoveries force astronomers to reconsider whether galaxy formation follows different rules in the early universe, or whether our models simply underestimate the efficiency of cosmic construction during the universe's youth. Fact 100. JWST studied Stephan's quintet. Stephan's quintet, a visual grouping of 5 galaxies engaged in a cosmic dance of gravitational interaction, became a showcase target for JWSTs to reveal the complex dynamics of galactic encounters. 4 of these galaxies are truly interacting, their gravitational influences stripping away gas, triggering star formation, and reshaping galactic structure through forces that operate over millions of years. JWST's observations revealed the shock waves, gas flows, and stellar formation triggered by these galactic collisions, providing insights into how galaxies grow and evolve through mergers and interactions throughout cosmic history. Fact 101. It revealed shock waves from colliding galaxies. The galactic collisions within Stephan's quintet create massive shock waves that heat gas to millions of degrees and trigger new episodes of star formation, cosmic violence that shapes galactic evolution on the largest scales. These shock waves represent some of the most energetic phenomena in the universe, galactic-scale sonic booms created when galaxies collide at speeds of hundreds of kilometers per second. JWST's infrared observations can detect the heated gas and trace the complex flows of material as gravitational forces reshape entire stellar cities. These cosmic collisions provide laboratories for understanding how galaxies merge, grow, and evolve over billions of years. Fact 102. JWST studied distant black holes. The supermassive black holes that lurk at the centers of distant galaxies become visible to JWST through the intense radiation emitted by matter falling into their gravitational embrace, revealing these cosmic monsters across billions of light years. These observations help astronomers understand how black holes and galaxies co-evolve, with the central black hole's activity influencing star formation throughout the host galaxy, while the galaxy's growth feeds material to the central black hole. JWST can observe these active galactic nuclei across cosmic time, tracing the evolution of black hole activity from the early universe to the present day. Fact 103. It measured star formation in young galaxies. JWST's observations reveal the furious pace of star formation in young galaxies, where gas-rich environments and frequent galactic mergers create conditions ideal for rapid stellar birth. These measurements help astronomers understand the cosmic star formation history, how the rate of stellar production has changed over the universe's lifetime, and why star formation was much more active in the past than it is today. The telescope can measure star formation rates across cosmic time by observing galaxies at different distances, creating a timeline of stellar productivity that reveals how the universe's ability to create new stars has evolved over billions of years. Fact 104. It provided new insights into dark matter. WST's observations of galaxy formation and large-scale structure provide indirect but crucial evidence about dark matter, the invisible material that comprises most of the universe's mass, but interacts only through gravity. By observing how galaxies form and cluster over cosmic time, JWST helps astronomers understand how dark matter halos grow and merge, creating the gravitational scaffolding upon which visible matter organizes itself into the cosmic web. These observations test our understanding of dark matter's properties and behavior, potentially revealing whether this mysterious component of the universe behaves exactly as current models predict. Fact 105. Its discoveries continue to rewrite textbooks. Every major discovery from JWST forces astronomers to reconsider fundamental assumptions about cosmic evolution, stellar formation, planetary systems, and the nature of the early universe, creating a cascade of revisions to our understanding of how the cosmos works. Textbooks written just a few years ago now contain outdated information about galaxy formation timelines, exoplanet atmospheric composition, and stellar nursery dynamics. The pace of discovery means that our understanding of the universe is evolving almost as quickly as JWST can point its golden mirrors toward new targets, ensuring that the coming years will bring continued revelations that challenge and expand human knowledge of the cosmos. Fact 106. JWST's gold is worth less than $10,000. The entire gold coating on humanity's most expensive telescope is worth less than a decent used car, demonstrating that JWST's value lies not in its materials, but in the precision with which those materials were applied. This modest amount of precious metal, distributed across 25 square meters of mirror surface with nanometer precision, enables discoveries worth billions in scientific knowledge. The irony is delightful. A telescope worth $10 billion uses gold coating, valued at less than what many people spend on their morning coffee in a year. This fact reveals something profound about modern technology. Value increasingly resides in information, precision, and capability rather than raw material costs. Fact 107. Its mirrors are the size of a dining table. Each of JWST's 18 mirror segments measures roughly the size of a large dining room table, yet polished to precision that makes a traditional mirror seem crude by comparison. Imagine sitting down to dinner on a surface smooth to within nanometers, reflective enough to bounce infrared light across billions of light years with minimal loss. These hexagonal tables, when properly arranged, create a collecting area larger than most studio apartments, all dedicated to gathering ancient photons from the edge of the observable universe. The domestic scale comparison makes JWST's achievement more tangible. We've essentially launched a house-sized collection of perfectly polished dining tables into space. Fact 108. The telescope was tested in giant cryogenic chambers. Before JWST could operate in the cosmic cold of L2, it underwent testing in giant refrigerators on Earth, massive chambers capable of cooling spacecraft-sized objects to temperatures approaching absolute zero. These cryogenic test facilities represent engineering marvels in their own right, creating artificial environments that mimic the thermal conditions of deep space, while allowing engineers to verify that every component functions properly at operating temperature. The testing process required months of gradual cooling and warming cycles, ensuring that JWST's complex mechanisms would deploy and operate flawlessly in the frigid environment, where it would spend its entire operational life. Fact 109. Engineers shook it to simulate launch. JWST endured vibration testing that simulated the violent shaking of rocket launch, ensuring that every component could survive the brutal acceleration and acoustic pummeling required to escape Earth's gravity well. These tests subjected the delicate telescope to forces that would destroy most precision instruments, verifying that beryllium mirrors, gold coatings, and complex mechanisms could endure launch stresses without degradation. The irony is striking. An instrument designed for the gentle precision of cosmic observation first had to prove it could survive being strapped to a controlled explosion and hurled into space at tremendous velocity. Fact 110. The telescope has a tiny nameplate with signatures. Hidden somewhere on JWST's structure is a small nameplate bearing the signatures of key personnel who contributed to the telescope's development, a modest human touch on humanity's most sophisticated cosmic observatory. This nameplate represents the thousands of engineers, scientists, technicians, and administrators who devoted decades of their lives to making JWST possible, their names now traveling through space as permanent passengers on the telescope's cosmic journey. It's a touching reminder that behind every technological marvel are human beings whose dedication, creativity, and perseverance transform dreams into reality and launch them toward the stars. Fact 111. Its instruments are shielded from micrometeoroids. JWST operates in a cosmic shooting gallery where tiny particles of space debris travel at velocities that turn dust grains into high-energy projectiles, requiring sophisticated shielding to protect delicate instruments from constant bombardment. These micrometeoroid shields represent a balance between protection and functionality, thick enough to stop most impacts, thin enough not to interfere with observations. The shielding design acknowledges that space is not empty but filled with debris from comets, asteroids, and cosmic dust, creating an environment where even microscopic particles can cause significant damage when traveling at interplanetary velocities. Fact 112. One micrometeoroid has already struck a mirror. Despite all protective measures, JWST has already experienced its first battle scar, a micrometeoroid impact that permanently damaged one of its primary mirror segments, creating a tiny crater in the precisely polished beryllium surface. This impact occurred during the telescope's first year of operation, reminding astronomers that space is indeed a hostile environment, where even the most sophisticated engineering cannot provide complete protection. The damage, while permanent, represents only a tiny fraction of the mirror's total collecting area, and demonstrates both the inevitability of space debris impacts and the remarkable resilience built into JWST's design. Fact 113. The impact caused minor but permanent damage. The micrometeoroid impact created a small but irreversible change in one mirror segment's optical properties, a permanent reminder that JWST operates in an environment where even microscopic particles can cause lasting effects. However, the damage affects less than 1% of the telescope's collecting area and can be partially compensated for by adjusting the positions of other mirror segments. This incident provides valuable data about micrometeoroid flux in the L2 environment while demonstrating JWST's robust design. The telescope continues operating at full capability, despite sustaining damage that would be catastrophic for less well-engineered instruments. Fact 114. Its mirrors are designed to handle small impacts. JWST's engineers anticipated micrometeoroid impacts and designed the segmented mirror system to remain functional even after sustaining multiple small hits over the mission's lifetime. The 18-segment design provides inherent redundancy. Damage to individual segments can be partially compensated by adjusting the remaining mirrors, ensuring that the telescope maintains its observational capabilities throughout its operational life. This damage tolerance represents sophisticated engineering that accepts the inevitability of space debris impacts while minimizing their effect on scientific productivity, allowing JWST to continue making discoveries even as it accumulates the scars of operating in the cosmic frontier. Fact 115. JWST's data is freely available to the public. Every image, spectrum and measurement captured by JWST becomes freely available to researchers worldwide after a brief proprietary period, ensuring that humanity's investment in cosmic discovery benefits the entire global scientific community. This open data policy means that discoveries made by one research team can be verified, extended, and built upon by scientists anywhere in the world, accelerating the pace of astronomical discovery through collaborative investigation. The democratic approach to cosmic data ensures that JWST serves all of humanity, rather than just the institutions that funded its construction, making the universe's secrets accessible to anyone with the curiosity and skill to analyze them. Fact 116. Anyone can apply for observing time. Scientists from any institution anywhere in the world can submit proposals to use JWST for their research, making this billion-dollar instrument democratically available to the global astronomical community. The competitive proposal process ensures that observing time goes to the most scientifically valuable projects, regardless of the proposer's nationality, institutional affiliation, or previous access to major telescopes. This open access policy transforms JWST from a national project into a truly international scientific resource, ensuring that the best ideas drive the telescope's scientific program rather than political or economic considerations. Fact 117. JWST's first images were released in July 2022. The public release of JWST's first science images in July 2022 marked a moment of global celebration as humanity got its first glimpse of the universe as seen through the telescope's revolutionary infrared eyes. These images, from the deepest infrared view of the cosmos ever captured to detailed portraits of stellar nurseries and dying stars, demonstrated JWST's capabilities while inspiring millions of people worldwide. The release represented the culmination of decades of work and the beginning of a new era in astronomical discovery, with each image revealing cosmic details that had never been observed before. Fact 118. The release was broadcast worldwide. The unveiling of JWST's first images became a global media event, broadcast live across television networks, streaming platforms, and social media channels, allowing millions of people to witness the moment when humanity's newest cosmic eye opened for the first time. This worldwide broadcast transformed a scientific milestone into a shared human experience, with people around the globe simultaneously seeing unprecedented views of star formation, galactic evolution, and cosmic structure. The global celebration reflected the universal human fascination with exploration and discovery, demonstrating how space science can unite people across cultural and national boundaries. Fact 119. The telescope has inspired countless artworks. JWST's images have sparked an explosion of artistic creativity, with painters, sculptors, musicians, and digital artists drawing inspiration from the telescope's revelations of cosmic beauty. The infrared palette of JWST's images, translated into visible colors for human appreciation, creates alien landscapes that seem both scientifically accurate and artistically compelling. Artists worldwide have incorporated JWST imagery into everything from abstract paintings to symphonic compositions demonstrating how scientific discovery enriches human culture by revealing new forms of natural beauty that expand our aesthetic sensibilities. Fact 120. Some call it the Time Machine Telescope. The nickname Time Machine captures JWST's unique ability to observe the universe as it existed billions of years ago, with every distant galaxy representing a window into cosmic history. When JWST observes objects 13 billion light-years away, it sees them as they appeared when the universe was young, effectively allowing astronomers to study cosmic evolution by looking backward through time. This temporal perspective transforms astronomy from a study of the present universe into an investigation of cosmic history, with JWST serving as humanity's time machine for exploring the deep past of space and time. Fact 121. JWST could detect signs of alien life. The telescope's extraordinary sensitivity to atmospheric chemistry positions it to potentially detect biosignatures, chemical combinations that might indicate biological processes on distant exoplanets. Oxygen combined with a water vapor or methane in disequilibrium with carbon dioxide could suggest living processes that maintain atmospheric chemistry far from chemical equilibrium. While JWST wasn't specifically designed as a life detection instrument, its capabilities for atmospheric spectroscopy could make it the first telescope to provide evidence of biological activity beyond our solar system, answering one of humanity's most profound questions about our place in the universe. Fact 122. It may spot oxygen, methane, or water on other planets. The detection of these key molecules in exoplanet atmospheres would represent different pieces of the habitability puzzle: water indicating the potential for liquid chemistry, oxygen suggesting possible photosynthesis, and methane indicating either geological or biological activity. JWST's spectroscopic capabilities allow it to identify these molecules across interstellar distances by analyzing how they absorb specific wavelengths of infrared light during planetary transits. Each molecular detection expands our understanding of planetary diversity while bringing us closer to identifying worlds that might harbor conditions suitable for life as we understand it. Fact 123. Its lifetime depends on its fuel supply. JWST's operational lifetime is ultimately limited not by the degradation of its instruments or mirrors, but by the amount of fuel available for maintaining its position at L2 and pointing toward cosmic targets. The telescope requires periodic thruster burns to maintain its halo orbit around L2 and to counteract the tiny pushes from solar radiation pressure and gravitational perturbations. Conservative fuel management could extend operations well beyond the planned 10-year mission, potentially providing 15 or even 20 years of cosmic observations if controllers can minimize fuel consumption through efficient trajectory planning and precise maneuvering. Fact 124. Careful course corrections could extend it to 20+ years. The precision of JWST's launch and trajectory has left more fuel than originally expected for station keeping and pointing operations, potentially doubling or tripling the mission's planned lifetime through careful fuel management. Every perfectly executed maneuver, every efficient trajectory correction, and every fuel-saving pointing strategy could buy additional years of cosmic discovery. The prospect of extended operations means that JWST could observe cosmic evolution over decades, watching astronomical objects change and evolve while providing continuous observations that span significant fractions of human lifetimes. Fact 125. JWST orbits with a halo-like motion around L2. The telescope follows an elegant halo orbit around the invisible L2 point, tracing graceful loops in space that maintain optimal positioning for cosmic observation while minimizing fuel requirements. This orbital choreography represents a solution to complex gravitational dynamics, allowing JWST to remain in Earth's shadow while avoiding the gravitational instabilities that could pull it away from L2. The halo orbit ensures that JWST never passes directly behind Earth or the Moon from the Sun's perspective, maintaining continuous solar power generation while preserving the thermal environment essential for infrared observations. Fact 126. It has already produced petabytes of data. JWST has generated more astronomical data in its first years of operation than many ground-based telescopes produce in decades, creating a vast digital archive of cosmic observations that will keep astronomers busy for generations. Petabytes of data represent millions of images, spectra, and measurements that capture the universe in unprecedented detail across enormous ranges of cosmic distance and time. This data treasure trove ensures that JWST's scientific impact will extend far beyond its operational lifetime, providing raw material for discoveries that may not emerge until decades after the telescope itself has completed its mission. Fact 127. JWST will eventually drift into deep space after its mission ends. When JWST's fuel finally runs out and its mission concludes, the telescope will begin a slow drift away from L2, gradually leaving the gravitational harbour where it revolutionized our understanding of the cosmos. Unlike Earth-orbiting satellites that eventually fall back to our planet, JWST will continue travelling through interplanetary space, becoming a monument to human achievement wandering the solar system. Millions of years from now, this golden mirrored ambassador of human curiosity will still be travelling through space, carrying with it the instruments and technologies that first revealed the infrared universe in all its ancient glory. Perhaps someday, far in the future, another civilization will encounter this drifting testimony to humanity's cosmic ambitions, a message in a bottle floating through the vast ocean of space, bearing witness to the moment when our species first learned to see the universe with infrared eyes and discovered our cosmic heritage written in the light of distant stars. And so our gentle journey through 127 boring facts about the James Webb Space Telescope comes to a close. Somewhere out there, at L2, 1.5 million kilometers from Earth, this golden-eyed sentinel continues its patient watch over the cosmos, gathering ancient light from the universe's most distant reaches and transforming it into knowledge that expands our understanding of everything. Thank you for drifting with me tonight through the remarkable tale of humanity's most sophisticated cosmic observatory. Whether this journey has helped you find rest or filled you with quiet wonder at the telescope that shows us galaxies from the universe's dawn, I'm grateful you joined me among the facts that reveal our species' determination to see deeper into space and time than ever before. Sweet dreams and clear skies. This is the sleepy astronomer, wishing you the most peaceful rest under the same stars whose ancient light now falls upon JWST's golden mirrors, carrying stories from the cosmic beginning to our curious eyes below.